All right, so yesterday we took a look at roots of quadratics. And again, a quick recap there. Roots of a quadratic are the same thing as solutions or zeros and are also x-intercepts if we think of it graphically. Today we're going to look at another way to solve quadratics, and that method is going to be by factoring. Okay, so a couple of really important things for factoring. In terms of solving a quadratic by factoring, we have to use what's called the zero product property, where we would have some quantity A times B equal to 0. The only way that this statement is true is if either A or B equals 0. So if I can factor something that's set equal to 0 and have it written as simply a product of factors, I can then set each factor equal to 0 and solve it. So with a quadratic, our goal is going to be to write that quadratic equation as a product of linear factors. So maybe x plus 1 times x minus 3. We're going to undo the FOIL process of multiplying and distributing that out so that we have it in terms of linear factors, so I can set each of those factors equal to 0 and solve. Okay, so all the ones that we're going to see today are pretty well set up to be straightforward. We're going to use a method that I call the sum and product. Okay, so what we're going to be looking, if we're thinking about something in terms of y equals ax squared plus bx plus c. So when a is 1, we're going to look to use sum and product. Okay, what do I mean by that? If we look up here at the very top right example, I want two numbers that add together to give me positive 3, but multiply together to give me a negative 10. So it might be a little bit trivial, but we'll go through. So my factors of 10 would be 1 and 10 and 2 and 5. Now, since the product has to be negative, 1 needs to be positive, 1 negative. So my pair that would add up 1 positive, 1 negative to positive 3 would be 2 and negative 5. So what I can then do is rewrite this, if it's set equal to 0, as x minus 2 times x plus 5. And again, now what that allows me to do is to set each individual factor equal to 0. Right, so we're going to have x minus 2 equals 0 and x plus 5 equal to 0. And from here, now I solve each of those individual factors. On the left, I do that by adding 2 to both sides, and on the right, I do that by subtracting 5. So I get two solutions here of x equals positive 2 and x equals negative 5. So again, we want to write that. We could either leave it as x equals 2 and x equals negative 5, or write it in set notation using curly brackets, x equals 2 and negative 5. And I guess I should actually do that in the other order, from least to greatest, so negative 5 and 2. All right, so what I want to do, I'm going to go through, I'm going to do the odds in the examples, just for the sake of time. The evens are all in the notes key. You guys can take a look at that. You just won't have necessarily my explanation for all of it. So let me zoom in here and we'll take a look at number 1 next. So again, before I do anything, I always want to ask, is there a GCF for all 3 terms? Okay, here there's not. For most of the ones we're going to see today, there aren't. There are a few examples, but not many. Okay, so no GCF in this case. A is 1. So again, I want to look at sum and product. Here is pretty easy. I need two numbers that multiply together to give me 3 and add together to give me 4. Since 3 is prime, the only factors that could possibly be are 1 and 3. Right? Think about it, if I were to FOIL this out, I would get x squared plus 3x plus 3. And if I combine those like terms, I get my original polynomial here, x squared plus 4x plus 3. So at this point, again, now I can set each of my factors equal to 0, because I have this expression completely factored, right? It's written as a product of factors equal to 0. The only way it's true is when each of these factors equals 0. And on the left, when I subtract 1, I get x equals negative 1. And on the right, when I subtract 3, I get x equals negative 3. So what we get here is x equals negative 3 and negative 1. Okay. Let's move down to number 3. Again, I asked, do I have any GCFs? In this case, I don't. I want to know, do I have any factors that will multiply together to give me negative 2? So one will be positive, one will be negative, and add to a positive 1. Those factors are going to be x are going to be positive 2 and negative 1, which will give me two factors of x plus 2 and x minus 1. Again, now that I have that completely factored, I can set each factor equal to 0. So we get x plus 2 equals 0 and x minus 1 equal to 0. And again, at this point now, I'm going to solve each individual linear factor. We're going to subtract 2 on the left. It's going to give me x equals negative 2. And I'm going to add 1 on the right, which is going to give me x equals positive 1. Again, when I write that in set notation, we're now going to have x equals, in curly brackets, negative 2 and 1. Moving on to number 5. Again, do I have any GCFs? In this case, no, I don't. So now I want two numbers that are going to multiply together to give me positive 21 and add to negative 10. So since the product is positive, both factors will have the same sign. Since they have to sum to a negative number, I know they both have to be negative. So let's say, for brainstorming purposes, I couldn't come up with the factors right off the top of my head. I want to make a list, right? Factors of 21, 1 and 21, 2 doesn't, 3 does, 3 and 7, 4 doesn't, 5 doesn't, 6 doesn't. We've got our entire list. Okay, two factors here that same sign, and add to negative 10 would be negative 3 and negative 7. So again, I can then write x minus 3 times x minus 7 all equal to 0. Again, I want to split this up and write two factors, set them each equal to 0. So x minus 3 equals 0 and x minus 7 equal to 0. At this point, again, now I'm going to solve each individual factor. So I'm going to add 3 on the left and get x equals 3. And I'm going to add 7 on the right and get x equals 7. Once I have that, again, I'm going to write it in set notation. So we're going to have x equals, in curly brackets, 3 and 7. All right, moving on to example number 7 here. Again, any GCFs? In this case, no. A is 1, so sum and product. I need two numbers that multiply to 10 that also add to 25. So here it's actually going to be 5 and 5. 5 times 5 is 25. 5 plus 5 is 10. So I'm going to have x plus 5 times x plus 5 equal to 0. So again, just like before, I want to set each factor equal to 0. So x plus 5 equals 0 and x plus 5 equal to 0. Now, in this case, I'm going to get the same thing each time. I'm going to get x equals negative 5 twice. Okay? There is actually significance to the fact that I get the same solution 2 times. For right now, we're not going to get into that, but there is a significance to that happening. Now, the one thing, I don't have to list the solution 2 times. I only have to write it once here inside of my curly brackets. Okay. The other thing I could have done at this point, instead of here, I could have just written this as x plus 5 quantity squared equal to 0. And then, because that factor was squared, set just that one factor equal to 0 and get my solution of x equals negative 5. It would have worked out the same. But again, for our purpose, it really doesn't matter which way we go about doing this at this time. Let's look at number 9 here. So number 9, I've got a quadratic again in standard form. A is 1. If I go to do sum and product, notice that right now in ax squared plus bx plus c, c is 0. So I would need two numbers that multiply together to give me 0, but add to negative 8. Doesn't really make a whole lot of sense, does it? So let me back up to something I've said a couple other times up above that we haven't actually had happen yet. Do I have a GCF? Here I've got an x squared minus 8x. The one thing that's common to both of these terms is x. When I factor that x out, I'm left with x times x minus 8 equal to 0. And in this case, I now have an expression that's completely factored. If whatever was inside my parentheses here, if this still had a squared term in it somehow, then I would still need to factor that part of the expression farther until it's completely factored. But here, it's completely factored. So I'm going to set both of these equal to 0. The first one's easy. I'm going to set x simply equal to 0, and I'm done. X equals 0. The second, I'm going to have x minus 8 equal to 0. And now I'm going to go ahead and try and solve it. So what I'm going to do, I'm going to add 8 to both sides of my equation. And I'm going to get x equals positive 8. This is going to give me two solutions. They're going to be x equals 0 and 8. If we move down to number 11, I'm going to have pretty much the same kind of thing here. A is no longer 1 though. Okay, so when a is 1, for right now, it's really going to be a big key that we want to look for a GCF. Again, here I have a constant or a C term that is 0. It doesn't exist. So GCF is definitely something I should be on the lookout for. So 6x squared minus 12x equals 0. My common factor here is 6x. When I factor out a 6x, I'm left with x minus 2 equal to 0. Again, I look inside of my parentheses and ask, is this expression completely factored? And in this case, it's a linear factor, so yes, it is. All right, so now I want to set each individual factor equal to 0 so that I can solve this. On the left, I have 6x equals 0. If I divide both sides by 6, 0 divided by 6 is 0. On the right, if I add 2, I get x equals 2. Again, for two solutions here, x equals 0 and 2. Let's take a look at number 13. Number 13, I have x squared minus 64. Let me write this in a slightly different way because I think what I'm going to do next is going to make more sense. I have x squared plus 0x minus 64 equal to 0. Okay, I'm missing that b term, I'm missing that first degree term, so think of it as being a 0. So again, do I have a GCF? No. A is 1, so I want to try sum and product. Right? Can you come up with two numbers that multiply together to give me negative 64, but add to 0? And again, if you're not sure, you can always make a list of factors. So like 1 and 64, 2 and 32, 3 doesn't, but 4 and 16, 5 doesn't, 6 does not, 7 does not, but 8 and 8. Now, I need them to multiply to negative 64. So one's positive, one's negative, and their sum has to be 0. So here we're looking at negative 8 and positive 8. So this is going to give me factors of x plus 8 and x minus 8. Which brings me to another point real quick. Even though I wrote them down here as negative 8 and 8 on my list, and then I wrote them as factors as x plus 8 and x minus 8, multiplication is commutative, right? 2 times 3 is 6, just the same as 3 times 2 is 6. So the order in which I list my factors here really doesn't matter as long as my factors are correct and complete. Okay? So at this point, it's completely factored. I can set each factor equal to 0 and go ahead and solve them. So in my first case, I'm going to subtract 8, and I'm going to get x equals negative 8. In my second case, we're going to add 8 and get x equals positive 8. For two solutions of x equals negative 8 and 8. Okay. For right now, we're actually going to skip number 15, okay, because it involves another type of factoring that we haven't necessarily talked about yet. Actually, you know what? I'm just going to do it anyhow. So one thing we could have done up above there, right? I had two terms that were squared terms. a squared minus b squared, right, set equal to 0. This can factor into what's called a difference of squares. Give myself a little bit of room here real quick. Oops. So a squared minus b squared, this is what we call a difference of squares. This factors to a plus b times a minus b. So let me come up here just for a minute. I had the x squared minus 64 equal to 0. In this case, I could write x squared as, well, x being squared. It's kind of trivial. But if you ask yourself what number squared gives you 64 out of 8 squared. So here I can get two factors then. A is x, b is 8. And if I then follow my form down here, a plus b times a minus b, then I get x plus 8 times x minus 8, which were actually my two factors that I had over here. So I got that same factored form, both from sum and product, as well as a difference of squares. So anytime you have, and if we look here at number 15, anytime you have a x squared and a constant and no first degree term in there, so no x to the first, you can always ask yourself, can we do a difference of squares? So in this case here, right, what quantity squared is going to give me 4x squared? And that quantity is going to be 2x all squared, right? 2 squared is 4, x squared is x squared. Minus the quantity squared that gives me 81 is 9. So I get 2x all squared minus 9 squared. So 2x is a, 9 is b, and factoring by difference of squares, I get 2x plus 9 times 2x minus 9. I can set each factor equal to 0, so I get 2x plus 9 equals 0, and 2x minus 9 equals 0. Now in this case, I'm going to have multiple steps. In the left, I'm going to subtract 9 on both sides. I'm going to have 2x equals 9. And when I divide both sides by 2, I get x equals, 9 halves, or 4.5. And on the right, I'm going to add 9 to both sides, and I get 2x equals positive 9. And then when I divide by 2, I get x equals 9 halves, or 4.5. Okay, I'm going to leave them as fractions for right now. And again, when I write that then as in set notation, this on the left, I made a mistake there. This should be a negative 9, which is going to give me a negative 9 halves. Okay, so we're going to have negative 9 halves and 9 halves. Again, or x equals negative 4.5 and positive 4.5. The next section is equations that are not already in standard form. So again, the one thing that I really need to do is to put it into standard form before I can factor it. Right now I have x squared plus 4x equals 21. I can't necessarily factor this yet because it's not set equal to 0. And technically there's an infinite number of ways that I can multiply two numbers together if I were to factor that and get a result of 21. Okay, so this needs to be set equal to 0 before I actually attempt to factor and solve the equation. All right, so I'm going to subtract that 21 over. I'm going to have x squared plus 4x minus 21 equal to 0. Okay. All right, so now I want two numbers that multiply together to give me negative 21 that will add to positive 4. Okay, those two numbers are going to be positive 7 and negative 3. So we're going to get factors of x plus 7 and x minus 3, still set equal to 0. So at this point now I can set each individual factor equal to 0 and solve. So x plus 7 equals 0, and x minus 3 equals 0. On the left, I have x plus 7 equals 0. So I can subtract 7 on both sides. So I can solve for x and get x equals negative 7. On the right, I have x minus 3 equals 0. So if I add 3 to both sides, it'll get x by itself and give me x equals 3. So again, here now I get my two solutions when I write them in set notation. Inside curly brackets, I have x equals negative 7 and 3 for my two solutions to this equation. Okay. I'm going to do the same or similar thing to number 19. With number 19, I've got x squared minus 5x minus 64 equals 7x. So again, I need this set equal to 0 before I do anything. So I need to subtract 7x on both sides to move it over here to the left. Okay. When I do that, negative 5x minus 7x, I'm going to end up with x squared minus 12x minus 64 equal to 0. Okay. So now I want to try and come up with factors of 64 of negative 64, pardon me, that add to negative 12. So I'm going to come up with a list of factors here real quick for 64. All right, so we're going to have 1 and 64, 2, 32, 3 doesn't, 4 and 16, 5, 6, and 7 don't, then 8 and 8. So I need a combination of one positive and one negative that sum to negative 12, and it's going to be 4 and negative 16. So my two factors here are going to be x plus 4 times x minus 16 equal to 0. Again, now it's completely factored. I want to set both factors equal to 0. So we have x plus 4 equal to 0 and x minus 16 equal to 0. All right, on the left, I'm going to subtract 4 on both sides to solve. We're going to get x equals negative 4. And on the right, I'm going to add 16 and get x equals 16. So here we get two solutions. They are x equals negative 4 and positive 16. We have one more on number 21 here. So I've got x squared equal, or 11x squared, pardon me, equals x squared plus 8x. Again, I need it set equal to 0, so I'm going to move everything over to the left. So I'm going to subtract x squared on both sides. So 11x squared minus x squared is going to give me 10x squared. And I'm also going to subtract 8x. It's going to be 10x squared minus 8x equals 0. So let me come back to one of the things we always should check for first. Do we have a GCF? Right, I've got a 10x squared and an 8x squared, or an 8x, pardon me. And in both cases, I have an x. I do have a numerical GCF here as well, so it's going to be 2x. When I factor out a 2x, I'm going to be left with 5x minus 4 equal to 0. Again, now I have this completely factored. It's written as a product of linear factors, so I can set each factor equal to 0. So I get 2x equals 0 and 5x minus 4 equal to 0. On the left, it's pretty straightforward. I'm going to divide both sides by 2. I'm going to get x equals 0. On the right, I'm going to add 4 to both sides. It's going to give me 5x equals 4. And when I divide both sides by 5, I'm going to get x equals 4/5, or 0.8. Again, I want to write this in set notation for my solutions. So we're going to have x equals, and in curly brackets, 0 and 4/5. Or I could write it as x equals 0 and 0.8. Okay. Ideally, the fraction's probably better. Okay, it's more exact here. It's still a precise decimal, but we want to get in and stay in the habit of leaving things in fractions whenever possible. Okay. You guys can take a look at the even examples here. They are in the notes key if you would like to go through them and copy them down, or some other ones to try where you have a complete solution written. Okay. One thing I want to point out is here in step 2, the guided notes tell us essentially to move everything to the left side. So you have essentially the equation, the quadratic on the left equal to 0 on the right. You don't necessarily have to move it to the left. It doesn't really matter if it's on the left or the right. The one thing I would tell you is ideally you want to move it to whichever side is going to give you a squared term that is positive. Okay, I don't really want to deal with a negative x squared out in front when I'm trying to factor. If that's the case, I'm going to move everything to the other side, or I'm going to multiply everything by -1, simply so that I can simplify my life a little bit in the process of trying to factor and solve. So what you guys are going to do for homework is in our 2.5 homework, it should be, scroll too far down, it's homework number 5, solving quadratics by factoring, day 1. Okay, I do want you guys to do all of them. And I'm looking to see if I want any of them excluded. Numbers 19 and number 20. They're doable, all right, but they're going to make you think a little bit. Okay, so I want you guys to try all of these. Really, the only way you're going to get good with factoring and solving quadratics is through practice and repetition. Okay, so it might seem a little tedious, but we're going to be doing lots of these over the next couple of days. Okay, so please give them a shot. If you get stuck on a couple of them, we can go over some questions on Monday, and but plan on moving on to some other techniques in terms of factoring quadratics when we come back after the weekend. All right, have a good one.